to discuss some of other types of paradigms, and for completeness sake only we are discussing these paradigms with the assumption that you have the basic knowledge of paradigms. And here we like to mention about the type of problem we handle under different types of paradigms. So the second paradigm what we like to discuss today is greedy method. Okay. Now here let us assume that there are n possible entity, and you want to find out the best solution using these n entities. Okay. Now say A1, A2, An entities, and now you have to select one by one so that you get the best possible solution for your problem. So initially you have say if I write the algorithm greedy, genetic algorithm for greedy, and A and n parameters, then you will be writing that your solution initially is phi, which is null solution, and then you have to select one after another. So for I equals to 1 to n, and then x equals to select one parameter out of n, and you check whether by selecting x that solution, this will lead to a feasible solution or not. If x leads to feasible solution, of your problem, then you update your solution by solution union x. Otherwise, you discard x. Otherwise, you discard x. That means that this x will not lead to the feasible solution. Okay, this is a simple strategy we follow under the greedy strategy. Now, one example is that I don't know whether you have seen the tapes, magnetic tapes. These are a large size, and we used to store the data or file into these magnetic tapes. And suppose you have the files F1, F2, F3, and Fn files, and the size of this file is S1, S2, S3, Sn. Now we like to store these files into the magnetic tape in such a way that it takes the minimum amount of time. Okay. So suppose I have the three files, F1, F2, F3, and the size of the file is say 20, 10, and say 5, or 20, 10, and then 50. So if I start saving the first file of F1, then F2, then F3, then the total number of record movements in that magnetic tape is that first time it will be saving a file F1 of size 20 records, and then it will rewind back. So second time, if I store the F2, so first it will move up to this, and then it will write again 10. So here you need 30 record movements, and third time. So it will go 30 and then 15. So you need 45 record movements. The total number of record movements becomes 20 plus 30 plus 45, which is 95. Okay. Now, if I think the other way, that no, I will store first F2, then F1, then F3, what happens? First time 10, second time it is 10, and then 20. So this becomes 30. And the third time, these 30 movements plus 15. So this gives you 45. Okay. That means 10 plus 30 plus 45. This gives you 85 record movements. Now what happens if I save the files in the form F2, F3 and then F1? What happens? First F2, which is the 10, next time it is 10 plus 15, it is 25, and then next time it is 45. So it becomes 10 plus 25 plus 45, it becomes 70, 80. Okay, and this is the minimum number of records to be moved to store all these three files into the magnetic tape. So what is the strategy we follow here? That you have n files, F1, F2, Fn, and with the size S1, S2, Sn respectively. The x initially solution is 5, and for I equals to 1 to n, and now you will be selecting x for from the set of n, you will be selecting the file which is the smallest in size. Okay, so S1 is the solution, and is it fully? Yes, it will lead to the solution. So you are storing it and your solution. So sol becomes sol union x1. X1 is x, which is the smallest file size, and then next time again you take get the next smallest one and you add it and so on. Okay. So this is the one strategy. This is the greedy method to solve the problem of storing the files into the magnetic. Now the next problem is well known to you, which is knapsack problem. Okay, do you know what is knapsack problem, right? Is it clear? If not, let me tell you what is knapsack problem. Let us assume that you have that n entities x1, x2, x3, xn, and to select xi you want the profit pi. Okay, so you have the profit p1, p2, p3, pn. To select pi you want the profit pi. To select xi you want the profit pi, and each entity has certain weights. Say W1 is the weight attached to x1, weight x3, and weight a. Now there exists a bin of capacity, a bin capacity f. Now problem is to select sum of x's and put them into this bin whose capacity is n, such that you earn the maximum profit. Okay, so what is the problem? Problem is to select some of the x's and put them into the capacity bin of capacity m in such a way that you earn the maximum profit. Right? So basic problem is that if I sell W3 weight or WI weights of item of xi, then I earn the profit pi, and I want to maximize my profit, but with the condition is that my bin can take up to the load of m unit of weights. Now one thing should be clear to you, that my bin, if it is not full, then I should take some more items from here to get to put into the bin, so that I earn little more profits. Okay. So I can write that maximize this problem. I can write maximize pi xi I is equals to 1 to n, such that, or subject to the condition, summation over wi xi I is 1 to n is less than equals to m, and xi is lying between 0 and 1, and weights are positive, right? So what happens? The problem is that I have x1, x2, xn are the entities, pi is, wi is the weight attached to xi, and pi is the profit attached to the item xi, and you have a bin of capacity m. You want to select some of the xi such that your bin is full, and also you want the maximum profit. So the problem can be redefined: maximize summation pi xi I equals to 0, I equals to 1 to n, subject to the condition that summation over wi xi less than equals to m, and xi is 0 and 1. What does it mean xi is lying by 0 and 1? That it is 0 if you don't select. If it is 1, you select the whole item. Whole item means that you select wi weights total, right? Or you can select small amount of wi of the xi ith component or ith item. Now how to solve this problem? So let us consider one small example. Suppose I have 3 items, item 1, item 2 and item 3, and the item weight is, 1 is having the weight 5, this weight is having 10, and this weight is having, say, 4. And I earn the profit is, say, 10. Here it can be 15, and it can be 8, 7, 6. No, it can be say 7. Okay. So this is your weight and this is your profit. So that means that if I sell 5 unit of item 1, I earn the profit 10, and if I sell 10 unit of item 2, I earn the profit 15. 4 unit of item 3, I earn the profit of 7. Now I want to, and I have a capacity of, say, 8. Now how to select this 8 unit of materials? Right, one possible thing, that I select item 1 completely and 3 unit from item 2. That means 5, 3 and 0. Another one can be 2, 6 and not 6, say 2, 4, 2, maybe one possibility. There are another possibility could be 3, 3, 2 and so on. If it is the case, then how much I earn the profit, or what is the profit amount? So I earn 5, so I earn 10, then I 3, that means 15 divided by 10 into 3. Okay, so this gives you, so 14.5. Now in this case, 10 divided by 5 into 2 plus 15 divided by 10 into 4 plus 7 divided by 4 into 2. So this is 1, this is 4 plus 1.56 plus 3.5, so it is 13.5. Here 10 by 5 into 3 plus 15 by 10 into 3 plus 7 by 4 into 3, you get 6 plus 4.5 plus 3.5, 8, 14, and so on. So you observe that this gives the better profit among them. But how to select, or what should be the best possible way to select or weights so that your bean is full and I earn the maximum profit. So one possibility is that because here you observe that we have considered that weight as a factor. Weight is related with my profit, so I should obtain what is the per unit profit. Now let us find out the per unit profit, that is P by W. So it is 2, it is 1.5, and this is 1.75. This is 1.75. Okay. So if that means that I must put as much as I can from the item 1 into my beans. Okay, because I am getting per unit profit is maximum on item 1. And if it is the case, so I will take 5 unit of item 1. Then next item is coming this one, because this gives the per unit profit is maximum. So what I should do, I should take 3 units directly from here. 3 units directly from here, so that, and 0 unit from here, so that you get the maximum profit. So if it is your selection is like that, then your earned profit 10 plus 0 plus so you earn the profit 15.25, which is the maximum profit you can earn. So if I consider the generalized problem, that you have P1, P2, Pn is profit with reference to item I, you have the weight Wi, then the selection procedure is that you first obtain the per unit profit for each item. And after obtaining the per unit profit, then you select first the unit having the maximum profit and try to put as much as you can into the B. Now, after putting that maximum profit here, you get the next highest profit one and try to put as much as you can into the B, and so on. Finally, you will get some fraction will be there of the ith one to put here. And if I add this, you will be getting the maximum profit. So that is the greedy strategy for finding the knapsack problem, for solving the knapsack problem. Now let us consider another interesting problem, that is optimization patterns. Now what is the problem here? Problem is that suppose I have files F1, F2, F3, Fn, and the size is S1, S2, S3, S7. So you have n files, and file I has the size or has the records number SI. Now the problem is that we want to merge all these files and to make into one file. Now you observed in the last class we discussed about the merging of two files. Then there is a need of data movement from that, from one file to another file. So if I have a file A and you have another file B and you want to merge these two files. Suppose this is of size n, this is size m, and first what you do that this you need n plus m record movements for merging these two files. Okay. So for this case also, that how if I merge F1 with F2, then I need S1 plus S2 the record movements, and then if I take this one, then you need again S1 plus S2 plus S3 data record movement and so on. Now that our target should be such, or our problem should be like that you merge these files into one file in such a way that number of records movement is minimum. There one way could be that you first merge these two, then you merge item with this one, merge item with this one, and then merge item with this one, and so on, right? The another way could be that you merge these two, this two, and this two, and this two, then merge with this one, and so on. There are several ways you can merge these n files, right? In order to understand the problem, say let us assume that I have 5 files, F1, F2, F3, F4, and F5. And size of the files could be 5, 10, 20, 15, and maybe this one is 30. So if I merge first this one, then this one, and then merge this whole file, and then this whole thing, then let us see how many record movements will be there. To merge these two files, you need 25 record movements. To merge this, again 25. Now to merge these two, you need 50, and to merge this with this, you need 80. So the total number of record movement becomes 25, 50, and then 80. So it is becoming 180 record movements. Now let us think about the other way. You have 10, 15, 5, 20, 30, and suppose I merge this one first, then this one, then this one, and then finally this one. In that case, here 25 record movements, here 30 record movements, here 50 record movements, and here 80 more record movements. In that case, total becomes 25 plus 30 plus 50 plus 80. So you get 185 record movements. Is it 185? 100, 185. Okay. Now what happens? If I first merge these two, then that merge item is merged with this one, then whole thing is merged with this one, and finally merge this one. In that case, here it is 15, here 15 plus 15, 30, here it is 20, and here it is 30. So number of record movement becomes 15, 30, 20, 30, not 30, yes. What is that? 15, then 30, and this becomes 30 plus 20, 50, and this becomes 80. 50, and this becomes 80. So this is 44, 95, 175. Now can you tell me what is the best way to do it? Yes. What you have to do is that you first try to get the file with the smallest size and you try to mark them. Then you select again file with the smallest ones and you try to mark. Say for example, suppose this is instead of 15, it is 25. Okay. In that case, instead of marking this one, you should have marked this two. Then it is becoming file size becoming 35. Now that this file, and this file, among these three, you consider the two of smallest one, these two are the smallest one, so which size becomes 55, and then you mark this two. Okay? So basically, if I represent in the form of tree, so what I will do, I will be putting first 5 and I merge with the 10, I get 15, and then I get 20. You get 35, and then this side you get 25 and 30, you get 55, you get 90. Okay? So the number of record movements will be 3 times of 5. 3 times. Okay? Because 5 has to move up to this. So 3 times of 5 plus 3 times of 10 plus 20 into 2 times plus 25 into 2 plus 30 into 2. Okay? So the effect is 15 plus 30 plus 40 plus 50 plus 60. This gives you 150, 150, 195. Okay? So that is the way you can solve this. So what you have done here, first thing is that you have picked up the 2 files with the smaller in size at the bottommost level, and then you merge them, and you fix up the 2 smallest files again, merge them, and so on. Okay? So formula becomes di into wi, where wi is the number of records in the ith file, and di is the distance of the ith record from the root. Now the next type of problem which we can solve through greedy method is finding the minimum spanning tree. Okay. Suppose G be the graph, weighted graph. Say okay, this is the weighted graph you have, and you want to obtain the a tree from this weighted graph. So the sum of the weight is minimum. Okay, and first thing is that if I forget about this, I'm looking for the spanning tree. then from this tree, from this graph, you have to find out the tree with n minus 1 edges and n minus 1 edges. That will give you the spanning tree. So for this graph, one spanning tree could be this one. Okay, so this is 10, 5, and 8. Another spanning tree could be this one, which is weight is 10, 7, and 5. Another spanning tree could be five, 7, and 8. Oh, sorry, not 7, it is 12. Okay. And the cost of the spanning tree is the sum of these weights. So the spanning tree having the minimum cost is known as minimum spanning tree. Now the two well-known, if you remember correctly, there are two well-known algorithms exist. One is the Prince algorithm, another one is Pushkal's algorithms. So let us discuss the Pushkal's algorithm, and let give you the graph. What is set of what is a V and E is the number of edges, and let us assume the number of vertices is n, and Wi or weight is assigned. Wi is the weight assigned to the edge between Vi and Vj. Wij is the weight assigned between Vi and Vj. Now since I have to obtain a tree, so let T be the tree. Initially it is null tree. Okay, and we have to finally obtain, if possible, a tree of having the number of edges as n minus 1. Now initially these weights, the edges are arranged in increasing order. Initially edges are arranged in increasing order, means with respect to their weights, right? Edges are arranged in the increasing order of weights. Okay. Now the algorithm will be like that, while the number of edges in the tree is less than n minus 1 and less than n minus 1 and is not empty. Okay, T is number of edges in the tree is less than not yet n minus 1 and is not empty. Select edge UV, the minimum cost. Okay. You select an edge from E having the minimum, from E having okay. Now you see, after selecting this UV, you have to see, can I put it in my tree T? What it means, that if I put it in my tree T, it should not create a cycle. Okay, that is the thing you have to see. So the check whether T union UV creates a cycle. Or not. If yes, then you cannot consider UV for your spanning tree, for your minimum spanning tree. You just discard UV. Discard UV from it. Else, it is not creating, you add is T union UV and delete UV from E. Okay? So that is your algorithm. So what it does, initially T is 5 while number of edges is less than n minus 1 and is not empty, select an edge UV from E, that edge must have the minimum cost, and then you see if I add this one here in T, it should not create a cycle. If it creates cycle, then you discard UV from E, and otherwise you add it into the tree and then delete UV from E. Now after coming out from this while loop, you check whether number of edges in T is n minus 1 or not. If it is n minus 1, you got the minimum cost spanning tree. So that is the Kuskel's algorithm. Now next paradigm is dynamic programming. This is also one of the most well-known paradigms of being used in different places. One simple one is that finding the all pair shortest paths problem. And here the strategy is like that. Suppose you have a graph with a graph G and you want to find the all pair of shortest paths. What you do, that given the cost matrix or weight matrix, that you see that by inclusion of kth node, whether your cost or path becomes shorter or not. If it is shorter, you consider. That is, the strategy is very simple. That suppose you have I at any instant of j, you have the shortest paths. You have the shortest paths via some nodes, some nodes, or via some vertices lying between 1 to k minus 1. Now, if you have at the k stage, what we do, that we like to introduce the node k and you check the path or weight of the path from I to k and k to j. If you find the sum of this weight is less than the original weight whatever you obtained from I to j, then instead of using this path, you now use this path. Okay, that is the idea. So dynamically you are updating your shortest paths. Suppose you have, in order to write this algorithm, suppose Cij is the weight of or cost of the edge ij. Now I don't want to touch this one, so I write for I equals to 1 to n, for j is equals to 1 to n. Say Aij is your Cij, and we'll update this Aij matrix for our work. The algorithm is for k equals to 1 to n, for I equals to 1 to n, for j is equals to 1 to n, Aij is replaced by minimum of Aij and Aik plus. Right? What is the physical meaning of that? That I am considering whatever the shortest path I have between I and j, using the vertices 1, 2, 3 up to k minus 1, and I have the shortest path from I to k using the vertices 1 to k minus 1 plus the shortest path using the vertices k, but between k and a using the vertices 1 to k minus 1, and that will be replaced by the that reality will be replaced by that value. Okay, this is the one thing. And similar type of problem is the traveling salesman problem, which you can solve using the binary, using the dynamic programming. Another problem generally we solve using the dynamic program is optimal binary search tree. Okay. Here what happens, the problem is that suppose you have the several identifiers, say ID1, ID2 and ID3, say ID8. There are n identifiers, and you know these identifiers we like to search several times. For example, in the case of compiler, you have started say if, then, else, these are the identifiers, and you have written suppose if one. Now I want to check whether if one is an identifier or not, so you will be searching it, right? Say for example, I have if, another one is then, another one is say and, another one is while, right? Say I have these 4 identifiers, so I can arrange these or put them in the form of binary tree. Say for example, if I write if is the identifier first, and this side will be end, this side it may be while, and this side it may be then. Another one could be, you know, I want to put here then, this side it is end, this side if it is if, and this side is your while. Another way I can put is that it can be say then, and this side it is if, this side is end, and this side is while. Okay? There are several other ways you can have your. Now suppose I want to check that whether if one exists or not. So what I'll do, I will search here. Now I'll come here if. Now I'll be looking whether there exists anything or not. If it is not, then you tell that this is not there. Now, similarly is the case with suppose while exists or not. Well, now you come here and yes, it exists, and it becomes a successful search. So there is a question of coming that number of comparisons you will be performing to find out whether an identifier exists or not. Okay. Now for this case, if it is a successful search, then average number of comparisons is required. For then is 1. For if it is 2 comparisons. For and it is 3 comparisons, and while is 2 comparisons. So this is 6 plus 5 is 11. 11 number divided by 4. So that is your average number of comparisons. Okay. But for this case, it is also 1, 2 plus 2 plus 3, and it becomes 5 plus 3, 8, 8 divided by 4, so it becomes 2. Okay, so this is that if I assume that they are equally likely, then for successful search it becomes 2.75 number of average number of comparisons. In this case it is 2, and in that case also it will become the 2.75 and so on. So our target should draw the tree in such a way that the average number of comparisons is minimum. Now here we assume that all of them are equally likely, and also we assume that it is only the successful search. But what happens in reality, suppose I go for if one, then it becomes a failure one, right? So there is not only that we are assuming that equally likely, which is not correct because it depends upon the programmer to programmer. So one part is that the question is coming that for identifier ID1, the probability of successful search is Pi, and there will be, you observe that if I have the 4 n identifiers, then there will be n plus 1 failure search. That if I have one item, say do, and in that case it will come here because it does not exist, so it becomes a failure search. So there will be Q0, Q1, Q2, Qi, Q0, Q1, and Qn, that many. That these are the probabilities for unsuccessful search. That means this will lead to this class of identifier, this will lead to this unsuccessful search leads to this class of items and so on. Right? So such that summation over Pi plus Qi plus Q0 is 1. Okay? Pi is the probability for ith identifier successful search, and Q0, Q1, Q2, Qn are the probability for unsuccessful searches. Then you have Q0 plus summation over Pi Q plus Qi equals to 1. Now, what is your problem? Now, problem is that you have to put the identifier in such a way that the cost is minimum. Cost means that if I put ith identifier in the level t, then ti, then you will be writing that pi into ti and so on. So the cost should be minimum. So this can be solved in using the dynamic programming. Now the next type of paradigms is backtracking and branch and bound. I think that this also I don't want to discuss much on this aspect, but what I want to tell that one problem is that graph coloring problems. Okay, so what you do that you have n vertices, you want to color one vertex by one color, and then they go to the next vertex and to put the color, another type of color, and you check that if by putting that color it fails to satisfy the criteria of graph coloring, then if it is, then go back and then go up, and previous node you just to put different type of color. So that is one example of backtracking. Similarly, the case of n-queen problems, that the problem is to put the queen on the chessboard, n cross n chessboard, in such a way that no queen attack the other queen. For example, I have a chessboard of 4 cross 4. And I have the 4 queens, Q1, Q2, Q3, Q4. Okay, so and 2 queens attack each other diagonally, or if I place them diagonally, or what is row wise, or they are putting in the same column. Okay, I have to put these 4 queens in such a way that they are not on the same diagonal, not on the same row, and not on the same column. So if I put Q1 here, Q2 cannot be put here, Q2 cannot be put here, cannot be put here, cannot be put here. So I cannot put Q2 here, I can put Q2 here. Okay, once I put the Q2 here, where shall I put Q3? I cannot put here. Okay, I cannot put here, 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 I cannot put here. Once I cannot put here Q2, Q3, and so what shall I do? So with the assumption, to simplify that assumption, let us assume that Qi is placed in the ith row. Qi is placed in the ith row. Okay, so Q3 should be placed here. Now once I know that Q3 position cannot be this one, cannot be this one, cannot be this one, cannot be this one, what shall I do? I backtrack. Now I try to put the position of Q2. So can it be here? Let us assume that Q2 is here. Now what happens? Q3 cannot be here. Q3 yes, Q3 can be here. So I put Q3 here. Right? Because it is not attacking by Q1, it is not attacking by Q2. Now what happens? Where shall I put? Where can I put my Q4? Can I put Q4 here? No. Q4 no. Q4 no. Q4 here? No. What shall I do now? Now you backtrack. Can I put Q3 here? No. Can I put Q3 here? No. Now can I put Q2? Q2 has gone, so I have to put Q1 in different place. So I have to put Q1 here. Now if I put Q1 here, where shall I put Q2? I cannot put here, 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 I can put here. Now if it is the case, where can I put Q3? Q3 I can put it here. If I put Q3 here, Q4 I can put here. So you observe that you get a solution where the no queen is attacking each other. Now there may be several, it is not the unique solution, you may have the different different ways to put these values or Qs in the chessboard to get the solution. Okay, so this is all about the backtracking. Similarly, you can find out the branch and bound and other things. Now, one thing I want to discuss is the traversal algorithm. This we need to know for our future studies. Now, the first problem is that suppose I have a binary tree and I want to traverse this binary tree. How we can traverse? Now, we tell this is the root and you have the left subtree and you have the right subtree. Okay. Now, in order to traverse this binary tree with n nodes, there are several ways you can traverse. One way could be that I traverse first root, then left subtree, then right subtree, and recursively I go for the left subtree root, left, right, and so on. Another one could be root, right subtree, left subtree. Another one could be left subtree, root, right subtree. Another one could be right subtree, root, left subtree. Another one could be left subtree, root, right subtree, root, or right subtree, left subtree, root. These are the 6 possible ways you can traverse your binary tree. Now, this is basically the mirror of this, so generally we do not consider this thing. So basically we have the 3 ways to traverse a binary tree. One is the root first, then left subtree, then right subtree. Another one is the left subtree, root, right subtree. Another one is left subtree, root, right subtree. So for example, if I have A, B, C, B, E, F, G, H, suppose you have this binary tree. Now, this traverse is known as pre-order traversing. This is known as in order, and this is known as post order traversing. Okay. So if I traverse pre-order using the pre-order traversing, then pre-order tells the root first, then left subtree, then right subtree. Now left subtree is this one. So if I have traversed, then B is, then left subtree, D, then G, then E, then H, then L, then K, then C, and then F. Now, if I traverse in order, then first is left subtree, then root, the right subtree. Now you have come here, first is left subtree, then root, the right subtree. Now you have first left subtree, then root. So it becomes that G, D, B, then H, L, E, K, A, C, F. And if I traverse post order, then left subtree, right subtree, and then root. Now left subtree, right subtree, then root, then left subtree, right subtree, so G, D, right subtree, left subtree, right subtree is L, H, K, E, B, F, C, A. Okay? So I think this you remember. We discuss all these things in your undergraduate curriculum. Now one thing you remember that if I know one of the either pre-order or post-order and in order, I can generate the binary tree uniquely. But this is not the case if I know pre-order and post-order but not the in order. Okay? In order to see that, suppose I know that pre-order and in order, let us see how we can generate the binary tree. See, from the pre-order, I can get who is the root of this node, which is A. Now, from the in order, I can find out that what are those elements in the left subtree and what are the elements in the right subtree. So this gives you that this much is on the left subtree, this much is on the right subtree. Now, from pre-order again, I can find out who is the root, which is B. Again, from here, I can find out this is the left subtree and this is the right subtree of B. So GD is here and this is here. Now from the GD, I get D, so I know that D is the root and G is D is the root, and from here you get G is the left of D, So it is G. Okay. Now once you know D, so I have done this one, I have done this one, this one, this one. Now I have this part, E is the root. So I write here E. Once I know the E is here, H and L is the left subtree of E. H and L, so H is the root and L is the right subtree. And E, K. K is the right of E, so K. Then you have C and F. C is the root and F is the right, so it is F. So similarly, if I have the pre-order and if I have the post-order in order, I can generate the binary tree uniquely. But in the case, if I have the pre-order and post-order, I am in problem. I know that from the pre-order, I can get the root of the tree, which is A, which is here. But after that, I don't know which are the elements in the left side and right side. So as a result, you cannot draw the conclusion of it. Now the next one is that traversing the graph. If I complete this one, then the preliminary of algorithms part is over, so that we can go for the parallel algorithm materials. So there are two ways we can traverse the graph. One is known as breadth first search. In short, we tell BFS. Another one is known as depth first search. In short, we tell BFS. So difference between these two is that suppose you have a graph. Suppose you have a graph, and what it does, that one is that you first go select this, visit this node, and then you visit all is adjacent, then for each adjacent, then you go to the next one, and so on. So it is a level wise basically you are searching. The other method is that no, you first search it, you come to this, then you come to this, then you finish this one, then you finish this one. That is known as depth first search. Hopefully you remember those things. But if I have to write the algorithm for breadth first search, say, we can write BFS, and B is the starting node, then visited B is 1, and I write U equals to V. Now for all vertices and also initialize Q to probability. For all vertices, U adjacent from U do the following. If visited W is 0, that means not yet visited, then add W in Q and visited W is set to 0, set to 1. Okay. So this comes under for loop, and if Q is not empty, delete U from and repeat this. Okay. So what it does, basically for all vertices W adjacent from U, do the following. If visited W is not yet visited, then you visit that one and you add W into that. And you repeat this thing for all adjacent vertices, that is the same level things. And if you find that Q is not empty, you take the delete one element from Q from the top and repeat this process, because you have to find out W and so on. But in the case of depth first, the idea is you have to go into the depth of the graph, and the algorithm becomes little different. DFS U and visited algorithm becomes like that. Visited V is equals to 1, and for all vertices W adjacent to U adjacent to V, because I consider here V, do the following. If visited V, visited W is equals to 0, then DFS W. Okay. Here it is that you check what we are doing, that you check with the visited DFS V. The visited V is 1, I am setting it first. Now for all vertices of W adjacent to V, you see whether W is visited or not. If not, then you call DFS W. Otherwise, you go to the next adjacent vertex or adjacent vertex of V and you check again, and so on. So that is the DFS or depth first search, and this algorithm is where you need to implement that shift. So with this, we like to stop here today, and we assume that we have discussed the different paradigms on sequential algorithms. So next class we'll be discussing about that need of parallel algorithms, different types of parallel models, and we'll start designing some algorithms. Thank you.